We're still talking about comparing means and standard deviations. And so we are up to case 3. And for case 3, we are assuming that each sample is different, but we are analyzing each sample using 2 different methods or 2 different instrumental techniques. And then the goal of case 3 is to check and find out whether the techniques are equivalent. So we're going to look at a journal article. They are interested in detecting tin ions in food samples. Tin is a toxic chemical and can enter food from tin cans. And so they wanted to detect whether or not the tin was there, and if so, how much. And in this particular journal article, they are comparing 2 different methods. They're using an atomic absorption spectrometer, and they're comparing it to an atomic emission spectrometer. So let's go ahead and switch over to that journal article. Okay, so table 4 is where they summarized all of their results. And this was a pretty comprehensive study. So if we look at the table here, we have total tin in canned food and fruit juice and 2 certified reference materials. So down here on the left-hand side, we see what the samples are, and they did 2 different techniques. So they tested the standard reference material and all of these different samples by themselves. So they just tested how much was in it, and then for these standard reference materials, they have a particular amount that was certified to be in it. And then they also spiked the sample with a certain amount of the tin to see whether or not they could detect that change. I think they might have a typo here. I think this 25 really should be 250. But other than that, everything looks good on the table. So the proposed method, this AAS, that's atomic absorption spectroscopy. The SF is for flame, which is a pretty common technique for atomic absorption spectroscopy. CPE stands for, just a second, I wrote it down. There, cloud point extraction. Cloud point extraction. So the cloud point is where you have 2 liquids that don't normally mix, like water and oil. And if you get the mixture to just the right temperature, it will start to mix and it will look cloudy right at the interface. And so this cloud point extraction technique is that you put your sample into this mixture and then you take it to just the right temperature. And at just the right temperature, the analyte that you're looking for will selectively go into that cloud point region where it's sort of mixing. And then you can just extract that part of it and then do your detection. And you'll see CPE all over the place if you are looking in analytical journal articles. So that's one of our 2 techniques, and this is the one that they were proposing as a new method. So you can see lots of cool information here. They have relative standard deviation, they have percent recovery, so that's comparing to how much was expected to be in the sample. And then the ICP-AES, ICP stands for inductively coupled plasma, and AES is atomic emission spectroscopy. So this was the method that they were comparing it to, that they felt confident of. And so this is sort of the known method that we want to know what we're comparing to. You can see they also did some students T testing and some F testing. I'm not going to talk about these columns here, but I have linked this journal article to the Moodle in case you want to look more carefully at it later, if you have time, of course. So let's go ahead and talk about how we would do case 3 to analyze method 1, the atomic absorption spectroscopy, with the atomic emission spectroscopy. So when we do case 3, what we're looking at is we're actually looking at the differences between the amount that is detected in each method. We're going to just ignore all of their uncertainties for this part of the analysis. So I'm going to switch over to Excel and show you how I did this. Okay, so I took a couple of minutes and I transcribed all of the samples here. So I just did, the number 1 was the plain one, number 2 was the one that has the spiked sample in there. And I just wrote down all of these numbers. So when we do case 3 and we're looking at the differences between these two techniques, we can just calculate that. If you're new to Excel, then the way that you calculate some basic math here is you start with an equals sign, and then you choose the columns that you want or the cells that you want to analyze. So I'm going to go ahead and do that for you live. So I would say equals, click on one of them, minus the second one, hit enter, and it will calculate that. And if I want to, so initially then these guys are all blanks, right? We'll just go ahead and recreate this Excel file for you. All right. So initially, this is the only calculation that I've done, but I want to repeat this calculation for all the samples. So I can either drag this little square all the way down, or if this column is right next to the other two, I can just double click on the right-hand little box there, and it will automatically do that calculation for all of them. So here I calculated the average. We already went through that one. And then we calculate the standard deviation for it as well. I went ahead and calculated the standard deviation by hand just to make sure that I was getting the same number, and we are. So I'm going to go back over to my OneNote and show you the equations for this, but it really is just calculating the standard deviation in the normal way. All right, so for case 3, we have method 1 numbers. In one column, we have method 2 numbers in the other column. And then, each one of these has, I guess I would have to say 1A and 2A and 1B and 2B and so on and so forth. Okay, so we have a set of different measurements. So for each of these techniques, we calculate the difference. So x1a minus x2a and on down. And then we're going to calculate the standard deviation of the differences. And so just like before, this is the sum of all of the individual difference values minus the average of those values squared divided by n minus 1. This is just the normal standard deviation. So when we do this calculation, for the Excel file I just showed you, I got 0.56 for my standard deviation. And then the t-test that we're going to do, we calculate the t-test based on the average d value, the average difference, over the standard deviation. I don't need a little bar there, sorry, too many bars. Okay, over the standard deviation of the difference that we just calculated, multiplied by the square root of n, which is the number of data points. So in this case, we have the absolute value of 0.11, which was the average difference. And if you go back in the video a tiny bit, you can see the Excel file, and you can see that that square in the column is minus 0.11. And then we're going to divide by the standard deviation, which is bigger than the average difference. And then we had 20 data points, and so we'll take the square root of 20. So if you calculate this t-value, this is 0.878. And as always, we are going to compare this to a t-table value. So our degrees of freedom is 19, and we don't have a table value at 19, but we do have a table value at 20. Which was 2.086. And we can see that this is a sufficiently big table value that our calculated t is definitely less than our table t. which means that our two methods in that journal article are statistically equivalent. This was at the 95% level. And so if I'm gonna go ahead and go back over to that journal article. Okay, here we are. So this is what they conclude. It's pretty clear that their data are really quite good and that their methods are equivalent to each other. So you can take a look at that journal article if you wish. But let's go ahead and take a look at another journal article, just for variety's sake, and see what we can find out about the journal article that we are looking at. So this next journal article, this one also is comparing atomic absorption spectroscopy. And look, there's the CPE cloud point extraction. They're using it for both of the different techniques that they're comparing. And they're doing UV vis, so ultraviolet and visible spectrophotometry, and comparing that to AAS. So in this particular journal article, which is also linked to the Moodle, this one is looking at detecting nickel in urine. And the big thing that they have in this journal article is that the nickel would be extremely dilute, and so they had to have a way of concentrating it. And that was what the cloud point extraction was for in this journal article. So again, you can take a look at the journal article if you have time. But what we want to look at in particular is this table 11. And so we have 5 different occupations. So they were looking at these occupations as ones that might expose you to nickel and therefore increase the amount of nickel in your body. So they did 14 samples by UV vis and 16 by AAS for people who worked in oil refineries. And they calculated the mean and standard deviation. I'm sure there's units around here somewhere. I'm not going to worry about it for right this moment. So if we look at all of these data, we have 5 different kinds of samples, and we really only have, we're going to have those 5 data points because they aren't giving us the raw data. They're giving us all of the means plus standard deviations. So when we do this analysis to calculate the differences, I'm comparing the differences for each type of career. Okay, so we'll go back over to Excel and do the analysis. All right, so I've taken a moment here to enter in the values for each of the different careers, and we're going to go ahead and calculate the difference. So just as we did before, remember, equals sign, subtract one from the other. It does not matter which one you subtract first, as long as you do the same thing each time, because the minus signs and the plus signs are going to get evened out. All right, we also need the mean value, so let's calculate that. And then the standard deviation. I just like to label my cells so that way I can know what I did later. Okay, now the other thing that Excel does is it gives you a whole bunch of decimal places, and like I showed you in an earlier video, if you come up here, I'm going to make sure we've got enough, we can see it. If you come up here, you can decrease the number of decimal places that you have in case you care about that. Alrighty, so we have a difference value and a standard deviation value, so let's go ahead and go back over and calculate what the differences are. So why don't you pause the video for a moment and go ahead and calculate the t value and see what you get. Okay, coming back together, we Well, I just wanted to comment. When I looked at these data, I wasn't super impressed by them. I thought, well, there's quite a bit of variability here, so I'm not sure whether or not these are going to turn out to be statistically equivalent. Also, the journal article itself, if you look at it, they're pretty cautious about what they say. They just kind of, like, the conclusion isn't very strong. I think they really needed an editor, but that's just me. All right, so getting back over here to OneNote, let's look at journal article number 2, and if we calculate the t-value, our average value for D was minus 2.5 times 10 to the minus 3. I just wrote that in scientific notation here. With a standard deviation of 0.012, we had 5 different industries, so N is equal to 5. And when we calculate this, I calculated 0.47, which looks pretty small, right? So our T table value for 4 degrees of freedom at the 95% confidence level is going to be 2.776. So this is greater than what the calculated one was, and so we can conclude that these methods are statistically equivalent too. So even though those data didn't look super great, they were good enough to be statistically equivalent, so that's great. All right, so hopefully this has been pretty easy to follow what we're doing with case 3. It's a relatively straightforward and simple test. Case 2 is really the one that requires probably the most calculation. Now, we have one more statistical test that we're going to talk about in this chapter. And in this chapter, or excuse me, in this particular test, this is a test that helps us decide how to deal with outliers. You've probably all had this situation before where you have taken a bunch of data and maybe 1 or 2 of your data points look a lot different than the other ones. And you think to yourself, should I get rid of this data point? Is that right? Would it be unethical for me to just drop this data point? And so we have the Q-test for answering this question. So, like all of our tests, we're going to calculate a Q, and it has a very simple looking equation. It just looks like gap over range. And there are tables, of course. And so what our goal is that if our calculated Q is less than our table Q, then we would not omit that data point. We would keep it. So I'm going to give you an example from my Chem 331 class, which is quantitative analysis. In that class, during this part of the semester, the students sometimes compare different colorimetric acid-base indicators to see whether or not they're equivalent. So they do a bunch of acid-base titrations. They are all analyzing the same sample, and it's approximately 0.1 molar. And I don't know going in, I just, ask the stockroom to make something kind of 0.1 molar-ish, and we usually take a whole bunch of old samples and throw them all together into one big bin so that everybody is analyzing the same sample. So one of my students, I happen to have quite a bit of old data, one of my students had this set of titration data. So they did 6 titrations that they reported, and these were the molarities. I think it's a sample of hydrochloric acid. Okay, so they've got 6 of these data points, and if we look at them, they all look pretty close to 0.1, except for this one, right? This one looks a little bit low. Is it too low? This one also actually looks a little bit high. Is it too high? So what we're going to do is we're going to do the Q-test here, and this allows us to illustrate what the gap is. So the gap is the difference between the outlier and its nearest neighbor. And this is an absolute value. We don't need negative signs here. We just want to know how far it is from its nearest neighbor. And then the range is the largest minus the smallest overall value in the set. Okay, so let's go ahead and calculate it for this particular data set and see whether or not either this low value is an outlier or this high value is an outlier, or maybe they both are. So let's go ahead and check. So we'll do the low one first. So the gap is going to be, what's the nearest neighbor? Let's check. Okay, this is the nearest neighbor. Okay, so we have 0.1010 minus 0.0940, which is 0.0070. And then the range, smallest minus largest. The smallest is the one we were looking at, which is always going to be the case, right? Our outlier is always going to either be the smallest one or it's going to be the largest one, because it has to be on an outlying point. So the difference between these two is 0.0126. So when I take the difference between these two, gap over range is Q calculated. And so when I look at that, I'm going to get 0.556. So we'll switch over to the book for a second and take a look at the table. All right, table 4.5 has a few values of Q at the 90% confidence. If you want a different percent confidence, all you have to do is look it up on the internet. There are lots and lots of tables out there, so you can find it. So as we recall, we had 6 molarity values. Notice that these observations here, this is n, not the degrees of freedom. So we do actually want this n is equal to 6 values. So the Q table value is 0.56. So let's switch back over now. Our table value, not T table, Q table, is 0.56. So you can see we are right on the edge of what would be acceptable. But we will go ahead and say that our Q calculated value is a little bit smaller than our table value. So we will keep the 0.0940 molar value. Okay. So hopefully this has clarified how you would do a Q test for checking on whether or not we should keep any data or keep an outlier. It's a pretty straightforward test, so I don't think you'll have any trouble with it. And let's go ahead and take some time to practice doing calculations with case 2 and case 3. So we'll make this into assignment number 5, which will be problems 414, 416, 418, and 422 out of the quantitative analysis book.